Thank you very much, Oleg, for the kind introduction, and then to the organizers for the invitation to talk today. So I'll be talking to you about the importance of reliability to the SunShot initiative. And I'll begin introducing the SunShot initiative, talk a little bit about where we are today, then talk about some of our analysis on the economic value of reliability, motivating why we care so much about reliability right now, and then by talking about our funding programs and priorities. So the SunShot initiative was launched in 2011. It was a national effort to make the cost of solar electricity, which at that time was about 4 times as expensive as conventional sources. So it was launched to bring the cost of solar to be competitive with these conventional electricity sources by the end of the decade. The cost target that we're working towards is 6 cents a kilowatt hour without subsidy by 2020. And if we reach these goals, the analysis suggests that solar could supply 14% of US electricity by 2030. It's pretty exciting. So where are we today? In the last 4 or 5 years, the field, the industry has seen tremendous change. And it's a time of dramatically increasing capacities. Costs are coming down dramatically as well. The cost of a photovoltaic module has come down about 64%. In the US today, we have 20 gigawatts of solar. That's enough to power about 4 million American homes. And this is about 10 times the solar we had just 5 years ago. Solar is a strong creator of jobs and economic growth. It employs about 174,000 workers in the US, a large fraction of those in installation. But this is more than steel manufacturing, automobile and truck manufacturing. So it's really becoming a significant industry. So I talked about the significant increase in capacity. This is shown here. So this is the cumulative installations that we have of photovoltaic modules in the US over the last 15 years. And you see that it's rising rather steadily. But you compare that to where we want to go by 2030. And you can see that we have still a long way to go. And we really, to get from where we are today to where we go, we need significant further innovation. Looking at this in terms of cost, this shows the levelized cost of energy, which is the present value of the cost over the lifetime of the system in cents per kilowatt hour for the 3 main sectors for photovoltaic power. On the left is residential, then commercial, and utility scale power. And for each of these sectors, it shows where we want to go in 2020. That's the right-hand side of the bar. And where we are today. Where we are today, the prices that you see on the market are the ones in blue. That's with the investment tax credit or with subsidies. And in red is the equivalent cost without the investment tax credit. So that's, since where we're trying to go is to make solar cost competitive without subsidy, what we really want to compare is the red bar on the left with the one on the right for each of the sectors. And just broadly speaking, what you see is we need about a factor of 2 decrease further in cost. So this brings me to the importance of reliability and the way that reliability can impact cost. So the way that work in reliability and durability impacts the cost of PV system is twofold. One is but through greater energy output over the system lifetime. So if you have less degradation of your system, if your system lasts longer, for the same system, you get more power out. So that in turn lowers the cost for each unit of power or energy. In addition, as we have a greater understanding of reliability, we can have better performance prediction. And this makes PV have lower technology risk. So right now, the cost of capital is a major contributor to the overall cost of photovoltaic electricity. And we can get to lower financing rates, lower cost of capital, by making PV a less risky technology. So I note on the slide that financing is also impacted by other factors, not just reliability, but reliability is an important factor. So to quantify this a little bit, this plot here shows cost on the y-axis. And the x-axis has the annual degradation rate. So each year in percent, how much the performance declines compared to the year before. The 2 lines here in green shows or the 2 lines have different discount rates and different lifetimes. So in green is a 7% discount rate. This is sort of a typical cost of capital for today. So the discount rate is effectively how much you have to pay to get that capital to do your project. So the discount rate, fairly typical for utility scale systems today, is about 7% and a 30-year lifetime. And in that circle, what you see is our sort of baseline for where we are today, about a 0.75% degradation rate. Now the red line shows a much lower cost of capital at 5% and a 50-year lifetime. So if we were able to both prove that PV cells lasted 50 years and if we were able to develop financial vehicles that could value that extra lifetime, where we could go in terms of cost. And so if we, in addition, improve the degradation rate, you can see simply, well not simply, but the impact of these changes in reliability is a 40% reduction in LCOE, and in fact, can actually get us to our SunShot goals. But it's also important here to note the reverse process as well. So reliability is an area where we're hoping that we're always making forward progress, but there's always the risk of reverse progress. As you know, choices might be made to cut cost, and in turn, these could hurt reliability. So the blue line shows if we as a net make PV a riskier technology and it has a higher cost of capital, a 10% rate, here we're still maintaining the same lifetime. But if the degradation rate goes up as well, you can see that we could easily have a 40% increase in cost here too. So reliability is a critical cost lever through these different factors. I want to look at this just another way. So we have done some analysis that looks at the sets of PV technology metrics that get us to the SunShot cost target. So this plot shows the module price on the y-axis, the module efficiency, or the system efficiency actually, on the x-axis. And every point on one of these lines, every point on this line gets us to the SunShot goal. So each line actually shows the relationship or trade-off between price and efficiency to get to the SunShot goal. So for example, at a 20% efficiency, you can have a 40 to 45 cent per watt module. And as you travel up to higher efficiencies, you can increase the module price, as you see. And as your efficiency gets lower, the module price has to come down significantly in order to still meet the SunShot targets. This line here is for an improvement in degradation rate from where we are today, about 0.2% per year in a 30-year lifetime. And what we can do here is look at, in this way, the impact of reliability. So if the lifetime goes from 30 years to 50 years, and again, if we're able to value that through our financial vehicles, we can have modules cost 25 cents a watt more. So the same module that we have today, if we could actually prove that it lasted 50 years instead of 30, we could buy ourselves a significantly higher price increase. Or if there are changes that could be made to these modules to make them last longer, to make them more reliable, they can actually come with increased cost. Conversely, if the degradation rate, this line in blue shows, goes back to a 30-year lifetime and shows a degradation rate of 0.75% per year. So if the degradation rate gets worse, there's a cost penalty. These systems have to be cheaper. And then the last line I'll show is actually maybe a more extreme case, but sometimes with emerging technologies we talk about, well, what if they only lasted 10 years? What if they degraded faster? But certainly there's room for that kind of a system too, isn't there? What this analysis shows is that if you have a 10-year lifetime, so a much shorter lifetime, a much higher degradation rate, these systems need to be a lot cheaper or much more efficient. In this particular illustration, 60 cents a watt penalty, it becomes very challenging. So again, all of this shows a different way of looking at the value of reliability. Another layer here is just in all of this, I've been talking about the degradation rate. And the degradation rate, typically we talk about it in the terms of a % per year, and so it's a linear degradation rate. And that is because, you know, some of our data that we have, I think much of our data, is sort of 2 points like we have here. There's an initial measurement, or at least there's whatever the panel that was purchased was rated at, and then there's a measurement later. and a line is drawn. And so you say, well, it's 0.5% per year. But what if degradation rate had a different shape? And for example, what if it looked like this? If it was 0% degradation rate for the first half of the system, and then it degraded by 1%. You can imagine mechanisms where that might be the case, but this is just illustrative. The delta here in total power out of the system, it's 3% more power if your system behaves in this way. But it actually, when you do the LCOE for system performance like this, it's a 1 cent LCOE difference. It's about 8%. And that's because capital has a cost to it, the value of power produced earlier in the lifetime is weighted more than produced later. So in this illustration, there's significantly more power earlier in the lifetime of the system, which causes the LCOE that comes out to be greater than the power delta. So it's important, and work is underway, to look at what is the true shape of performance in photovoltaic systems, and certainly different systems are going to have different shapes of these curves. But the better that we understand what these shapes are, the better we can predict performance. And in this illustration here, if we simply knew that the shape of the curve was more like the green than the blue, we actually could change the levelized cost of energy by knowing that we'd have more power out earlier in the system life. So that's some of the discussion around the way that reliability can impact the cost of the system. And I'll transition now and talk about some of the work that we've been funding and our funding priorities at the Department of Energy. So the program that I run is our Photovoltaics R&D subprogram, and we have three main thrusts in the program. It is improving reliability and durability, increasing efficiency, really increasing performance, and lowering manufacturing costs, lowering the materials costs, the processing costs. And of course, all three of these approaches wrapped together bring down the cost of solar electricity. That's the goal. What we fund in the reliability space, we spend over $10 million a year at our national labs at NREL and Sandia on work in reliability and performance. For those of you who've been in the reliability conference, you've heard several talks by folks from NREL and Sandia that we've been funding. This work includes the PV Quality Assurance Task Force that is run out of NREL. It includes work on emerging technology characterization. So newer technologies as they come up, how do we characterize them? What are their failure modes? All of the early characterization that's done to enable these technologies to have a better chance of getting to market. It includes degradation rate analysis. The plot on the right here is Dirk Jordan and Sarah Kurtz's famous paper looking at a comprehensive study of degradation rates that have been reported across the literature to come to giving us an idea of what number we should be using as a field. Also includes performance modeling and the regional test centers. So the regional test centers there's 5 centers, one managed by NREL and 4 by Sandia, and they're shown on this map. They are in Vermont, Florida, New Mexico, Nevada, and Colorado, so spanning different climate zones as well. And they provide a place for field validation of PV technologies, again, across climates. So you can install the same systems in different climate zones and see how the reliability and the performance is impacted. The labs provide technical staff for operations and maintenance, performance, and analysis. They're also looking at weather stations and things like soiling that's happening at these systems as well. This past year, we ran a funding opportunity that was open to the public called Predix2. And this funding opportunity was almost $10 million for reliability and durability research with a focus on better correlation of accelerated testing and lifetime prediction. This was actually a 4 to 5 time increase in the amount of funding that we have put out to the general field that's been available outside of just the national labs in reliability. So this was a major increase in our investment in reliability. And as you can see from the figure there, our goal is really to have systems that can be powering for decades. We will be making announcements for the projects that have been funded through this program in the next, within the next month or two. So you can look out for those. And these are expected to be about 3-year-long projects. I wanted to talk just for a moment more broadly about our funding priorities, and this is in part because what may be of interest to many of you, we will be releasing a funding opportunity shortly from my team looking at photovoltaics research and development topics, not just reliability, and in fact, spanning a wide range of areas. So just talking about some of our areas of increased interest so that you can hopefully start thinking about these things. So improved performance and reliability. We historically have had a lot of focus on efficiency, which is critical and still important, but we want to think about performance more broadly than just efficiency, but actually what are all of the ways that we can get more power out? So including optimizing for spectral sensitivity. So as your solar spectrum changes in different locations or throughout the day or throughout the year, are there ways to improve the performance that you get out of the particular system? Similarly, operating temperature and temperature coefficients, soiling, and of particular interest probably to this community is better ways specifically for light collection across angles, cheaper methods for light trapping, better and cheaper anti-reflection coatings, for example. We're looking for, as well, lower cost, higher performance designs that include reliability considerations. So the work we fund doesn't need to be specifically focused on reliability, but that should also be a design choice that we want people to be looking at as they're looking at innovation and technology. We're interested in what's possible by focusing on the PV module. So historically, we've had a lot of focus on just the semiconductor piece, the cell. But if we broaden our focus to include the packaging and the integration of the cells together electrically, how can we improve performance, reliability, and lower cost by looking at that picture? So advanced module designs and innovation in non-cell components. But again, our overall mission as an office is to lower the cost of solar electricity, and so we are really looking for all opportunities and all good ideas that make a case for how they can really impact the cost of solar to and beyond our SunShot targets. So I've talked about our SunShot targets of making solar cost competitive with conventional electricity sources, and that's our near-term target at DOE. However, we look beyond that as well, and as we get increased deployment of solar on the grid, which we hope to see, as we get increased deployment, because solar is an intermittent resource, there's going to be additional costs to deal with that intermittency. We're going to need storage or demand-side management, possibly better power electronics. All of those things are going to add cost. So as we go to longer term, so as we look towards 2030, what we want to do is to decrease the cost of solar even more significantly, well below grid parity, so that when we're looking for solar plus these costs for grid integration together, that can be cost competitive. And I just wanted to illustrate one pathway to, say, 3 cents a kilowatt hour that can be obtained through innovation in PV technology alone. So if we take where we are today at about 10 or 11 cents a kilowatt hour, and we about halve the module price, that gives us almost 2 cents. We improve module efficiency from the benchmark of 16% to 25%. That gives us a little over 2 cents a kilowatt hour. Now, of course, there are technologies out there that are already significantly higher than 16% efficient, but in this case, we're improving efficiency while achieving lower cost and all of these other pieces on top. We're improving reliability, lowering the degradation rate, and making the lifetime 50 years. This gets us 1.6 cents kilowatt hour. Reducing hardware and labor costs, so depending on the PV system design itself, it may enable reduced labor costs during installation, less needs for racking and mounting. So if those costs could be halved by our PV technology innovation, we get another 1.6 cents. And if we make PV less risky technology, we can get another 1 cent. And this gets us, just through innovation of PV technology, to 3 cents a kilowatt hour. So this is just one path. There are many pathways to get here, but just for what this could look like and what this could mean. So I'm getting towards the end of my talk, and I wanted to just make a pitch for coming to join us at SunShot. So we have a fantastic, motivated team of folks working to bring solar energy cost competitive with conventional sources by 2020. We have a great team of people. We are hiring for a number of positions. There's actually a position on my team that's open right now. This is the link on USA Jobs for anyone who might be interested. This is what's called a technology manager position. So it's a position where you're immersed in thinking about the next challenges for what we need to be funding and overseeing the projects we are funding. If you go to usajobs.gov, you can actually just search photovoltaic, and this will be the one that comes up. But please come and talk to me if you're interested in learning more about our office. And as I said, we do have positions in a number of areas that are open. So I wanted to end by thanking folks who contributed to this talk. The cost analysis work was largely done by Mike Woodhouse with help from others at NREL's Strategic Energy Analysis Group. And my team, Jeff Kinsey, who's highlighted, is our reliability expert who did some of the work reliability-specific analysis work I showed, and the rest of my team is shown here. And if you're interested just in staying up to date on what we're doing at SunShot, hearing as soon as our next funding opportunity comes out, for example, you can sign up for our monthly newsletter, which has a link, energy.gov/sunshot, and there's a box right on our website where you can sign up, and my email address is here as well, and I'm happy to take questions. Thank you.